So, good morning everyone. Welcome to Cake Scam, and in today's lecture, we are going to cover periodic properties and we are going to cover the entire portion from NCERT along with some important information from JEE and also the oxides part of this chapter. I will be uploading as a separate video. This should be enough for your JEE Mains, NEET or BITSAT. So, let's go on. Of course, this is not for first timers. I expect you to know that by now. And oh, I forgot to fill this. Anyhow. So this is the periodic table. This is the S block. This is P block. In between of them, there's transition of D block, and there's inner transition because they're inside the table. So this is F block. So yeah, I hope you know that. So let's first start with Moseley's law and modern periodic table. Basically, what happened, Moseley did an experiment and he threw fast electrons on different metals to get X-rays. And he noticed that the frequency of X-rays emitted, they held a relation with the atomic number of the metal he bombarded them on, which was the square root of frequency was equal to a positive constant into Z minus the screening constant. We will see this later. And square root of frequency was linearly proportional to atomic number, and this proved that atomic number is a more fundamental property than atomic mass. When he did it against atomic mass, this was the graph, and you can see it is perfect with atomic number. And in a periodic table, the horizontal rows, they are called periods, and the vertical columns, they are called groups. All the blocks are labeled in the diagram at the start. I showed you that. Now this is how you name basically this is a nomenclature of elements which have atomic number greater than 100. Note that these are not the official names. These are basically the convention that we follow to name the elements before an official name is claimed by a country or the discoverer of the element. So let's begin. Remember these root words for digits: nil, un, byte, try, quad, pent, hex, sept, oct, n for 0 to 9. And basically, you just combine those root words to make the name like this. You can see the table. Now let's shed some light on the groups of periodic table. If we look at S block elements, basically the number of valence their general configuration, it is ns1 or ns2, and their number of valence electrons is equal to the number of electrons in their ns shell, 1 or 2. The group number is equal to the number of valence electrons, so again 1 or 2, and they're reactive. They have low ionization enthalpy and they are never found in free state in nature because they are reactive. They react with anything, and they form ionic compounds except for lithium and beryllium. We will see why later. P block elements, they are ns2. ns2 is there, and np1, np2, all the way up to np6. Representative elements are p and s block together. For p block elements, the number of valence electrons is equal to number of electron in ns, so 2 plus the number of electrons in np, that is the group number. And the that is number of valence electrons, and the group number is number of valence electrons plus 10. So the possible groups here are group 13 to group 18. Helium is not a p block element since it only has 1s2 configuration, but it is still placed in the 18th group because it is a noble gas. And group 18 is, yes, noble gas. Group 17 is halogens. Group 16 is chalcogens. Group 15 is pnictogens. Group 14 is crystallogens, and group 13 is icosagens. Now D block elements, their general configuration is ns. This can be 0 to 2, and n minus 1d. Basically, it will be like 4s 3d, right? So the D subshell, it can be 1 to 10. The last electron enters D subshell, except for thorium, in which the last electron is in F subshell. But still we consider thorium a D block element. Ignore the kid in my background. Sorry, I hate kids. Anyhow, so group number, it is equal to the valence number here, valence electrons here, which is what? Number of electrons in ns plus the number of electrons in n minus 1d, the principal quantum number minus 1d. And the groups possible here are group 3 to group 12. You see here how group 1, group 2 were with s, and group 13 onwards was with p. So the numbers in between, they are taken up by d. This is further proof that the d block elements are treated as intermediate between the s and p block elements. And I told you that this ns can be 0 to 2. So it has 0 electrons only in the case of palladium, and all 10 electrons are here. And ns has 1 electron in case of chromium, copper, niobium, molybdenum, technetium, ruthenium, rhodium, silver, and platinum. Okay, this is in 3D series. These many are in 4D series and this is 5D series. Now F block elements, n minus, I think it forgot to render, but n minus 2f, this can be 1 to 14, n minus 1d 0 to 1, and n is 2. Okay, just remember that. I'm sorry. And lanthanoids are the top row. Like I showed you two rows of inner transition metals. So the top row is called lanthanoids, bottom is actinoids, and their valence electrons is ns plus n minus 1d plus n minus 2f. All the elements of F block are group 3. It is because all of them show third oxidation state, and actinoids are radioactive, and elements with Z greater than 92 are called transuranium elements. This is a guide on how to predict the period of an element. Look through it. I am positive you know that already. This is Bohr classification. We call group 18 inert gases. S and P block together are called representative elements. D block, except for zinc, cadmium, and mercury, are called transition elements. Since these are full subshell, they are not transition elements, but still we study them along with D block. And the F block elements are referred to as inner transition elements. This is an NCERT example of how we predict the periods and groups. So just look through it. And hydrogen does not have a fixed position in the periodic table because it resembles both group 1 and group 17. Now we finally come to the properties. So atomic radii first. Different types of radii are defined for different arrangements of atoms. See, most atoms can give one or more types of arrangements, but the thing is, for any element, there is only one most suitable type of radius. So what are the types of radius? First of all, covalent radius. What is that? It is this. It is half the intermolecular distance between a diatomic molecule with that atom, like H2Cl2 Br2. This is most suitable for what kinds of atoms? It is suitable for those atoms which can form a diatomic molecule with themselves, like I showed you here. And since like helium cannot form with itself, it is hard to define a covalent radius for helium. So we go for other types of radii. What other types? Well, one of them being metallic radii. It is taken as half the distance between metal cores in the lattice, if there is one. If there is a lattice, so lattice of course will have cores of metal. So that half the molecular distance between those cores, that is the metallic radii, like I showed you here. And then there's the, oh my god, how I hate children. Please ignore that. Uh, there's some kids crying in my background. That's all they do. Imagine spending 9 months in a womb and not learning calculus. Anyhow, van der Waals radii is the. Oh my god, wait, let me close the door. Much better. Now let's look at van der Waals radii. Van der Waals radii is defined for those atoms which are not in direct contact, like not in a lattice, and they don't have a fixed position, like they neither have a diatomic molecule or core or a lattice. Basically, they are not packed with each other. And an example of this is like gas atoms. And how do we define? It is half the average distance between two atoms in such an arrangement, which is like a gas. So you can see like here. And elements can provide more than one radius based on definition, and if that happens, the van der Waals radius is understandably greater than metallic, greater than covalent. And inert gases only give van der Waals radius. What are the trends in atomic radii? Let's see. In a period, all types of radii individually decrease left to right. Why so? Because increasing nuclear charge. With every step you take towards the right, the nuclear charge is increasing, which pulls electron with more force. The increasing nuclear charge overpowers the addition of a new electron as well, and that's why the radius usually decreases left to right. And what is atomic radii? We know covalent, metallic, and van der Waals. What is atomic radii? Basically, atomic radii refers to the most suitable radii for each atom. So, atomic radii for inert gas of period increases. Like increases in the sense it is defined in such a way which makes it appear bigger than the other atoms. Like look here. This is the normal uh, trend in the second period for any type of radius. But when we talk about atomic radius, we pick the most suitable one. And for neon, the most suitable one just happens to be van der Waals since it is an inert gas, and the other gives covalent, which is why they appear smaller than neon. And for D block, the radius it decreases left to right, but they increase at the very end. You must have seen the D block video. If not, go check it out. And the radius of 4D series and 5D series is very close to each other because of lanthanoid contraction. This is the graph of F block. 4F graph is shown, 5F is a smooth decrease. Like if you were to draw the graph of actinoids, it would go like straight down like this. But 4F has two exceptions because of half and fully filled orbitals, F orbitals. And in a group, it increases top to bottom because more shells are being added. Basically, if you are comparing any trend across a period, you are going to see the nuclear charge, how it varies. And if you are going to compare any trend in a group like vertical columns, then you are going to see the number of shells or the radii. Exception to the top to bottom trend increase is gallium, which is below aluminium in the periodic table, has a lesser radii than aluminium. Why? Because the d electrons, they are not able to protect the gallium from the nucleus, and hence it pulls the outer electrons too. Now let's look at ionic radii. It has the same trend as atomic radii in most cases, but some important details I'll tell you. Anion is always bigger than neutral atom, which is bigger than cation, and this has no exceptions. The smallest cation is H plus and the smallest anion is F minus, and H minus is exceptionally big, even bigger than Cl minus, Br minus, O2 minus, K plus, and it is only smaller than I minus. And remember that Li plus is greater than Mg2 plus, greater than Al3 plus. This was like JEE mains or advanced PYQ, I don't know. And for species with the same number of electrons, like if you balance charge and make them have the same number of electrons, so the radius decreases when atomic number increases. This is how it happens. Now let's look at ionization enthalpy. Basically, it is the energy required to remove electron from a neutral isolated gaseous atom or ion, and it is always positive for an atom. What does it mean to be positive? It means that you have to supply energy to an atom in order to remove its outermost electron, and it can be less than 0 for ions. For example, if you have an anion and it really wants to be a neutral atom, charge is always a destabilizing thing. So sometimes when you remove an electron from an anion, it can give or release energy in order to come back to its neutral state, because the neutral state happens to be more stable. And successive ionization enthalpies like I1, I2, I3, I4, they are always increase for any species. For example, what it means is that you can see what it means. If you were to keep removing electrons, every electron would be more difficult to remove than the last. And why we can abuse this fact. Seeing sudden jump of successive ionization enthalpy values, we can predict the number of valence shell electrons of the corresponding atom. Like whenever you see there is a big jump in removing the next electron, you get to know that the earlier state was more stable. Okay, and that's it. What factors does ionization enthalpy depend on? It decreases when shell number increases. Just read this, you know this already. And what are the trends basically? Well, first of all, in S and P block, the ionization enthalpy, it increases left to right. But there's some exceptions, of course. This is organic chemistry, inorganic chemistry. Basically, exception like here I have detailed 3 exceptions like this in second, third, and fourth periods, and 3 more in the group 15, group 16 part. How does it happen? Basically, these exceptions, like between group 3 and group 2, they are because that beryllium, magnesium, and calcium have full NS2 subshell, and it is difficult to remove an electron from those. And exception 246 is because of half filled subshell, p subshell in nitrogen, phosphorus, and arsenic. So I just told you that half filled and fully filled configurations have more ionization enthalpy. And if we talk about groups, the ionization enthalpy is usually expected to go down, like it is expected to decrease. Less energy should be required top to bottom in a group, but some groups have special orders, like group 13, Bombay to Goa, all are Indians, BTL, GA, AL, IN. And gallium is greater than aluminium because of poor shielding, as I told you. And indium is so less because of lanthanoid contraction. It is at the last, you can see. For group 14, it is normal order. very normal. But just at the end, while tin should be greater than lead, lead takes the lead, which is again because of lanthanide contraction. And for 3D series, if you were to number d block elements from scandium to zinc with digits like this, the ionization order would be this phone number, and remember this phone number. Isn't that cool? And lanthanide contraction is not observed in lanthanum because they don't have f electrons yet. Now, applications of ionization enthalpy. Low ionization enthalpy indicates that metallic or electropositivity is more, and it tends to react by loss of electron. I think that's easy to understand. And it also means that reducing power is high. What does that mean? What is reducing? Reducing means supplying electrons to somebody and losing electrons yourself. So if the process of losing electrons yourself is not that difficult for you, which means low ionization enthalpy, then you have a high reducing power. That is obvious. And for example, alkali metals, uh, they have this order of reducing power. But why is lithium so high? It is because of high hydration energy. Like ideally, you would have expected lithium to be below sodium, but no, because of high hydration energy, it is able to lose electron very fast because it wants Li plus to be very stable by the solvent. And high ionization enthalpy usually means an inert gas or an halogen. If difference of ionization enthalpy between two adjacent charged states of the same species is less than 16 electron volts, the higher charged state is more stable. But if it is greater than 41 electron volts, the lower charged state is more stable. I think that makes sense. Now let's look at electron affinity. Keep in mind, electron affinity is a positive quantity, but electron gain enthalpy is a negative quantity. So it is essentially electron gain enthalpy is just the negative of electron affinity at absolute zero. But I will be using these terms interchangeably. What is this? It is energy released when 1 mole of electron is added to 1 mole of neutral isolated gaseous atom, and it is also known as electron gain enthalpy, and that is represented as delta HEG. We use them interchangeably, but EGE is a better term because it follows thermodynamics conventions. Like energy released, then the sign must be negative. But this we follow the opposite condition if we look at electron affinity, and at absolute zero temperature, EGE is equal to negative of electron affinity, but at other temperatures, this is the case. Well, electron gain enthalpy is greater than zero if energy is absorbed, which means energy, if the species takes energy in the process, then electron gain enthalpy is greater than zero, and it is less than zero if energy is released. First electron gain enthalpy is spontaneous. I'll just say it like this. Adding an electron is spontaneous for everybody, the first electron, except for nitrogen, magnesium, beryllium, and group 18. And the second, third, fourth, yada yada, electron gain enthalpy of any atom is always non-spontaneous. These are the trends of electron gain enthalpy. Basically, electron affinity decreases down the group. What does that mean? It means that they have lesser and lesser tendency to have an electron added to them, so it decreases down the group, or we can say the EGA becomes less negative. However, there is an exception here. The third period elements in group 13 to 17 have more electron affinity than second. Why? Because they have an extra d orbital to accommodate electron, which to a second period does not have. Electron affinity, the tendency to take an electron increases left to right except for inert gases. And here's some exceptions. Basically, in any period, the group 1 will have greater electron affinity than group 3, which will have greater electron affinity than group 2. Okay, this is because group 2 being fully filled NS2. And look at this order. The electron affinity of group 14 is greater than group 15, except in the case of the last element of both groups. And what are the factors? It has the same factors as ionization enthalpy. Lastly, let's look at electronegativity. What is electronegativity? It is the tendency to pull electrons towards itself in a covalent bond. We denote it using Greek letter psi. And what are the factors? First three are same as ionization enthalpy, but it increases, like the tendency to pull electrons in a covalent bond increases when the percentage S character increases. What does that mean? Well, here S character is 50%, here it's 33%, and here it's 25%. You know this through chemical bonding. So sp carbon becomes more electronegative than sp2 carbon, which becomes more electronegative than sp3 carbon. And lastly, it increases when oxidation state increases. So this means that O2 plus will have more electronegativity If I'm not wrong, this has electronegativity of 11.4, very high. And this can be greater than O plus, greater than neutral oxygen. Basically, it increases when oxidation state increases. Think of it logically. It is losing electrons, so it has more tendency to attract electrons in the covalent bond. And electronegativity is not something you can just take an atom and measure, but instead we use many scales for it and we compare elements' tendency relative to each other, like percentile system in JEE mains, CGP something. Multiple scales are used like Pauling scale, Mulliken-Jaffe scale, Allred-Roschow scale. The most famous is Pauling and Mulliken. And remember this order of electronegativity of the periodic table. Fluorine most electronegative, followed by O, Cl, N, Br, I, S, C, selenium, then hydrogen. And these are the trends for the electronegativity, which have almost no exceptions. It is zero for inert gases, and other than that, they increase left to right and decrease top to bottom. Cesium and francium have the least electronegativity in the entire table, which is 0.7. Fluorine has 4. And here's the applications. In a covalent bond like this, you know Fajan's rules, there's ionic character. So that ionic character is given by this formula, where delta psi is the difference of electronegativity between the two participating atoms. And this compound, MOH, acts as an acid when electronegativity difference between oxygen and hydrogen is greater than the difference between oxygen and metal. And it acts as a base when this condition is met, the opposite of the previous condition. This was the entire chapter, and these are the NCRT extra points. Go through them. I will give you the PDF. I will soon be uploading a separate video on oxides. And lastly, here's a summary of all the trends. So, thank you for attending this video, and please share to your friends. That might help me fund my college fee. And I just love you guys a lot because the support in the past few months has changed my life. It has made me quite confident in myself, and I have been able to love myself a bit more. And that's it. Bye bye. Take care of yourself and your families.